Okay, so this was where we stopped last week. Okay, so I want to carry on with some of the more important superposition. Okay, so last week, right, we gone through 5 different flows. Right, you have your uniform flow, you have sink source, and then when your sink and source is too close to one another, right, it's called a doublet, and then we have a vortex flow. Right, then we went through this thing called the Laplace equation, where I showed you guys that when there are two flows coming together, we can actually add up the flows behavior together, but we cannot add up the velocities as it is, but we can add up things like the stream function or the velocity potential. Right, so the first thing that we did last week was to add up a uniform flow, okay, and a source and a sink, or source or a sink, sorry. Okay, so when you do that, right, okay, you can get a ranking half body. Okay, that's what you have done in the lab. Alright, and then from there you can get a few things. That means you can get where is the stagnation point, okay, and what's the thickness of the ranking half body. Alright, so that was the first thing that we have done. Now for today, okay, I'm just going to carry on with where we left off last week. Okay, so the second flow that you will see, right, okay, the first one was uniform plus source or uniform plus sink. Alright, the second that you will see actually is a uniform plus doublet. Alright, which I think you probably have done this in your lab also. Alright, so this is a little bit more complicated, okay, because in a sense, now we have almost 3 flow behaviors acting at one go. Okay, so for us to analyze the flow behavior, therefore there's a need for us to identify the stream functions first. Alright, so this is the stream function again because it's a pure axial flow. Okay, so this is a stream function that we get for axial flow, uniform axial flow. Okay, and this is for a doublet here. Okay, so sometimes, right, the question doesn't give you the equation, so you have to know the equations for each specific flow. Alright, sometimes they don't tell you what are the flows that's being superimposed together. Okay, they will just give the 2 equations, and you need to know, okay, what is this flow representing. Okay, so in this case, for a doublet, right, okay, so this is the equation for doublet. So this is your doublet strength, okay, and this is for your uniform flow. Okay, so when we add this up, okay, we can get this equation here. So there's a sum total of the stream function here. Okay, so this flow, right, is a little bit more interesting in the sense, right, when you have a uniform flow, okay, hitting against a doublet, okay, eventually, right, you have such a flow that's developing here. Okay, this is almost like a circle here. Okay, where the flow, right, will go past this circular shape here. Okay, so there's a certain characteristics that will cause this to happen. Okay, so when the 2 stream functions of the uniform flow and the doublet, right, the sum total when it equals each other, okay, the total stream function will become 0. Okay, and when this happens, okay, this circular shape will happen. Okay, so we are just flowing past, okay, a circular shape. Okay, in this case we call it a circular cylinder. Alright, so this is the characteristic that we always see. Okay, so you let the flow develop until a point where this plus this equals to 0. Okay, because there's a negative sign here, right? If this sum total is equal to 0, it just means that the value of this uniform flow will be equal to your doublet flow also. Right? That's why when the 2 stream functions are equal, okay, the total stream function will be equal to 0 here. Right? So when it becomes a cylinder here, there are a few things that is important. The first thing is, okay, you can actually know you can actually find out what's the radius of this cylinder here. Okay, so in the question, right, okay, the flow characteristics is to find what is this radius equals to. Okay, second thing to find, right, again, is the same as last week, okay, where you can find what's the stagnation point equals to. Okay, so we can do a little bit of analysis here. Okay, so everywhere around this circular shape, right, on this circular shape, the stream function will be equal to 0. Okay, so the question is, right, how do we actually find this radius r here? Okay, how do we find the radius r? Okay, so the first thing that we must know, okay, is that to find radius r, okay, the total stream function of the 2 flows we add together should be equal to 0. Okay, that's the first characteristics that you need to have. Second thing, okay, so we just weight the equation. Okay, the equation will just be equal to 0. So notice, right, in the previous slide, I put this as u small letter r, okay, with this r here. But the moment, right, we want to find what is a capital R, the small r becomes the capital R. Okay, because that represents the circular cylinder that we are looking for. Okay, therefore, right, the unknown that we have, right, actually is our R value. Okay, so if you make some numeric manipulation, right? Okay, you can get what's your R equals to. So your R really is just square root of K over 2 pi U. So K, this camber here, right, is your doublet strength. Okay, this U is your free stream velocity. Okay, so this R is dependent on both the doublet characteristics and also the uniform flow characteristics. Okay, so sometimes, right, we see R as this, or if you like, right, you can put it as R squared. Okay, so this is pertaining to this point here. Okay, that means when your stream function total is equal to 0. Okay, so therefore, right, instead of writing this equation here, we can actually rewrite our stream function total. Okay, so this is the definition that we have based on the previous slide. Okay, so when you see here, right, what we can do is that actually we can now further simplify this equation because there's a sine theta, there's a sine theta. Okay, there's a u and there's a u here. Okay, so notice, right, this equation now is all in terms of u and sine theta. Now, how do I get this equation? Okay, I get this equation because I sub in this value here, okay, onto this equation here. Okay, so instead of having a camber, okay, I don't want a camber anymore. Okay, I put it in terms of my R squared. Okay, so by doing this, right, okay, I have a u, I have a u, I have a r, I have a small r, I have a small r here. Right, so what can I do? I can actually take out some common factors. Okay, so my total stream function is equal to u r sine theta, 1 minus capital R squared over R squared. So this capital R here represents the radius of the circular cylinder. Okay, this R, right, is any point from the center of the doublet, okay, to the radius of the cylinder. Right? Okay, so this is quite an important equation because then we can actually do some okay, make some assumptions from this equation here. Okay, so this R sine theta, right, if you guys remember, is your polar coordinates. Okay, so why R sine theta is your polar coordinate? You can change our R sine theta in terms of Cartesian, which is your y. Okay, so we can write this as uy bracket 1 minus R squared over R squared. Okay. So let me just repeat. Okay, this equation here, okay, is no different from the previous slide equation. Okay, the only difference is that I substitute, okay, my kappa over 2 pi u, right, because of my R squared here. Right? Okay, so we have this equation here now. Okay, so I think you guys will recall this. Okay, I have my VR and my V theta. Okay, because the doublet, right, is a flow that is actually circulatory. So you have both the radial and our tangential velocity. Okay, so if you see, right, now we have found the total stream function to be equal to this. Correct? Okay, so how do you find radial velocity? It's quite simple, right? We have 1 over r here. We can do a differential equation, a partial differential equation to find our stream function here. Right, so if we do a differentiation, right, the only thing that you achieve actually is your sine theta here. Right? So if I do my VR, I'll get this equation here. Okay, and then similarly, right, if I want to find now my V theta, okay, I differentiate my stream function with respect to radius, okay, I'll get this equation here. Okay, so now it tells me, right, for a flow that has got both uniform and a doublet, okay, I have both radial and tangential components that I must consider. Okay, but the thing is, right, where does the capital R occurs? Capital R occurs at the surface of the cylinder, right? So that means, right, at the surface of the cylinder, my small r will be equal to my capital R. You all agree? Okay, because if you look back at the diagram, okay, this is your capital R, right, which is around the surface of the cylinder. The small r is measured from the center here, right? So there will come a point where your small r is equal to your capital R, right, which is at the surface of the cylinder. So therefore, right, when I go back to my equation, okay, if I say my small r is equal to capital R, right, okay, if you put that into this equation, what do you see? You see that your VR will be equal to 0, right? Because this over this is equal to 1. 1 minus 0, so therefore your VR will be equal to 0, right? What about your d theta? Will it be equal to 0? It will not, right? Because this over this will be equal to 1. 1 plus 1 is equal to 2, right? So that means your tangential velocity will be equal to 2u sine theta. Okay? So for a doublet, right, to find the velocity at the surface of the cylinder, okay, this is a two characteristics. Alright, so obviously, right, velocity is a vector. So these are the two components of my velocity vector. Right? So you can actually find the total surface, total velocity on the surface. Right? But given that my VR is equal to 0, right? Okay, that means the total velocity will still be equal to d theta. Agree? Okay? So then we have found actually the flow velocities component, right, of this position here, that is your uniform flow plus your doublet. Okay, but we learned something else. We learned, right, from Bernoulli's equation that if you know velocity, right, what can we find? We can also find the pressure values that we want to that we can infer from this value here. Okay, so in a sense, right, sometimes, okay, instead of finding the velocity, okay, it's also better for us to express answers in terms of pressure value. Okay, so what is the Bernoulli's equation? The Bernoulli's equation is this. Okay, P plus half rho U squared equals to P plus half rho. In this case, I put V theta squared. Okay, because on the surface of the cylinder, right, the only velocity component that is available is my V theta. Alright, so we know the definition for Cp. Okay, Cp is what? P minus P naught over the dynamic pressure. Right? So we can rearrange this equation to see if you take P minus P naught, that means it's equal to what? It will be equal to half rho U squared minus half rho V theta squared. Agree? Okay, so U here represents your free stream velocity. Okay, that means it's not at the surface, it's just a velocity at some point away from the surface of the cylinder. Right? This P naught here represents what? Your ambient pressure, ambient static pressure. Right? So this is both these two terms here is your reference pressure. Okay, but this value here on the right represents the pressure and velocity components on the surface of the cylinder. Alright? So we are just trying to relate our V theta, right, in terms of our Cp value. Okay? So this is the definition for our Cp. Okay, it's the pressure at any point I'm interested in minus the free stream pressure over the dynamic pressure. That's the free stream dynamic pressure. Alright, so we can see from here, right, if I have P minus P naught, I should have what? Half rho U squared minus half rho V theta squared. Okay, so instead of writing P minus P theta, P naught, we can write this as half rho U squared minus V theta squared. Okay, so you can see from here, right, actually, in fact, I can simplify this fraction further. Okay, break this into two fractions here. Okay, what do I have? I got one that's half rho U squared over half rho U squared, right? So the first term will be equal to 1, right? The second term, what do I have? Okay, I can break this into two fractions here. Okay, so in fact, right, at the end of the day, I can find a Cp, okay, just by knowing what is the tangential velocity on the surface of the cylinder. Yeah. Okay, so what is V theta equals to? Because now the previous slide, what do you form for V theta? V theta equals what? 2u sine theta, right? Okay, so since you know that V theta is 2u sine theta, okay, instead of writing in terms of V theta, we can further write this as what? Cp equals to 1 minus 4 sine square theta. Okay, so this is sort of like an analysis, right, on the surface of the cylinder when a uniform flow is superimposed with a double flow. Okay, so some of the things that they will ask you is what is the Cp value on the surface of the cylinder? Okay, therefore, right, this is the step that you can do. Or what is the velocity on the surface of the cylinder? Okay, in fact, right, they even ask you things like, okay, at perhaps 30 degrees, okay, what is the pressure coefficient at 30 degrees to the cylinder? Right, so we just need to put this as pi over 6 here. Okay, so you can get different Cp values, okay, along the surface of the cylinder. Okay. So this is for uniform plus doublet, okay? We went through uniform plus source of sink, okay, then we went through uniform plus doublet. Right, the last one that is the most important, right? Okay, or in fact the most complicated actually is this. You have uniform plus doublet, okay, then plus vortex here. Okay, so how do we do the analysis? It's the same thing, okay? You will have a flow feature and a flow feature here. Okay, how do you know is it a vortex or not, right? It's actually by this tau here. Okay, because when there's circulation, okay, there will be vorticity. When there's vorticity, right, you know that it's